All right, so what you're seeing here are solutions found to this bipedal walker problem by a new algorithm called POET. So as you might guess, the challenge is to keep this little thing here walking to the right as far as you can while it encounters various obstacles. And it is and remains a challenging reinforcement learning problem to have an agent learn to overcome various obstacles and walk well in different environments. So the paper we're going to look at is called POET. It's by Uber Engineering, and the full pronunciation is the Paired Open-Ended Trailblazer, endlessly generating increasingly complex and diverse learning environments and their solutions, by Roy Wang, Joel Lehman, Jeff Clune, and Kenneth O. Stanley, as I said, from Uber AI Labs. So as you already saw, the challenge they take on is this bipedal walker problem. Now, their method is very general and not limited to this problem, but this is the problem that they focus on. I'm going to jump some of the explanations here and dig right into the problem. As you can see, the problem is the following. You have this thing here, which is the walker, and it has two legs, and specifically it has 4 joints. So the 4 joints are here 2 and here 2. And you can give torque on all of the 4 joints. So it's basically a 4 output problem. And you do have sensors as input. So the inputs, I believe, is a LiDAR. So the LiDAR is this red line you see here. I think it has 16 of those in various angles. And also it has pressure detection on the feet, I believe, to see whether or not they are in contact with the ground. And it might also have an angle, so a gyroscope that tells you which angle with respect to the ground the head is. So you have various sensors on these things, and you're able to basically control what the legs are doing. And your goal is to make this go as far to the right and as fast as possible. You see the reward down here is -100 if the robot falls over. That means if the head hits the ground. And then it is 130 times delta x, that's how far you go to the right, minus the hull angle, and the hull angle, as I said, is this angle here. So you want to keep it as stable as possible, because if there's a difference in the angle per step, then you get penalized. And also you get penalized for each torque you apply. So you want to kind of apply minimal force on the joints in order to go very far. But by far the most important point is to go to the right as far and as fast as you can. There is an end here somewhere, and if you reach it, you get a score that is above 230, and they choose the limit of 230 here to determine. So if the agent gets 230 or more, then it has solved the environment. That's what they claim. That's from experience. So as you see, the environment has various obstacles here. There are holes that you can fall into that you need to jump or step over. There are these kind of stumps here. They can be of various height. So this is a bit shorter and this is a bit longer. And the general terrain has a roughness, and this can go to very rough from very smooth. So this is a parameterized environment, and obviously they are able to generate these environments from parameters. And the goal now is to have an agent that walks well in any environment that you can think of. Right, so here on the left you see this is very challenging down the stairs. This also isn't too easy because there's a gap here. And there are 5 parameters of these environments. So there is the general roughness of the terrain. That means kind of how many hills it has and how fast they're coming. There is the stump lower bound and stump upper bound, I believe, so how high the stumps are, and also how long the gaps are. And with these parameters, you control how difficult an environment is. So the straightforward thing to do is simply to, let's say, sample environments and have a reinforcement learn approach to this. And that usually doesn't work. I already want to see this without having talked about what the algorithm is. This is the approach where you try this thing. It's called evolution strategies, but you can think of it as just a straightforward optimization procedure. So there's an agent and there's an environment, and you're trying to solve the environment using just straightforward optimization. Now, the evolution strategies are not your classic RL algorithm, but you can compare it to it. It's just that these people, they like the more, I have a feeling they like the more esoteric learning algorithms. In any case, so you see in these environments, large gap, rough surface, and so on. These are supposed to be displayed in figures 3. So these 2 environments and also these environments here. The evolution strategy, so the classic approach, if you just straightforward optimize, they get very low scores on average, whereas Poet gets here very high scores above the 230 threshold. So what's happening? If you're trying to just solve these environments from scratch, you basically don't really have a big chance of solving them, because let's say you're here and you're trying to move to the right. You know, you might learn how to do this, and you see this from scratch solution actually manages to get to the right. But then as soon as you reach this, you're in this gap and you just fall down the gap, because all you've learned so far is how to move right? So what you would need to do is you would need to plan ahead, like what Poet does. You need to see that there's a gap. You need to plan ahead and already lift up a leg in order to then step over the gap here and then do a little jump right here. And this sequence of action, this kind of planning ahead, it is very difficult to learn this for a classic RL algorithm, because you basically get reward for everything you do. So initially you get reward for moving to the right, so that's 10 if you reach here, another 10 if you reach here, and so there is another 10 if you reach here, and another 10 if you reach here. Whereas if you lift up your leg, that's like -5, because now you've changed this angle, and we saw this is negative reward, right? So a classic optimization algorithm will always fall into the hole, because that is where you get the immediate reward. Whereas you'd have to do a sequence of action that doesn't give you a reward right now, but it gives you more reward later. And in order to learn this, you need a kind of a better algorithm than just straightforward optimization. So maybe I can explain this. If you have a maze, and here is the start, and here is the goal, and there is like walls, and the walls are something like this. What you need to do is go around here. But what a classic optimization algorithm does is always like, it goes here, because that's ever so closer to the goal, and then it just gets stuck because it can't fathom that it needs to go around here. So it needs to go farther away before it gets closer. So these people, we've talked about this before in like open-ended learning, novelty search. What you would want to do is you would want to gradually build up solutions that can explore the space, like to go here, go here, go here, and basically build up these solutions. And there are 2 components to what this Poet algorithm does. So the first component is curriculum learning. curriculum learning. What does curriculum learning mean? Curriculum learning means that you start off with easy tasks and you increasingly build up more and more and more complex tasks. So let's say I have an environment here, and I'm going to attempt to draw, and at the beginning we just kind of start off with this flat surface, right? And here is our little walker right here, and we'll just train it to move right on that, and that should be doable with kind of a classic approach. And then we gradually move to more difficult environments. So maybe we'll make it a bit more rough, right? And an agent that can already walk to the right already kind of has, think of it as a pre-training in like NLP. You can then get more and more challenging, and then maybe at some point you can build in a gap, right? So you build in one of these gaps, and now it already knows how to move to the right, and now it might learn to jump a small gap, right? If you make it small at the beginning, not like this one down here, there's a very large gap. But if you make it small, by accident it might stumble over it and then learn and continuously how to master the gap. So this is the curriculum learning approach. It means that from environment to environment, you get harder and harder challenges. So first flat, then more rough with a gap, and so on. The second approach, the second ingredient to Poet is what they call stepping stone learning, or transfer learning, or things like this. and that's where you kind of have to think of this not as a single agent optimizing, but as a population of agents. So let's say you do this curriculum learning, right? And you're getting fairly well here at rough terrains, right? More and more rough terrains. But you, in parallel, you also have a second optimization procedure. You also start out kind of flat, but with this thing, you go, as we said before, small gap. You keep it flat, but you just increase the number of gaps here, right? Gap, gap, right? Whereas over here, you just keep making the terrain rougher and rougher, right? So what the philosophy is that an agent that might, be able to master this rougher terrain, it might actually, that skill, because here this kind of looks like a gap here. The skill of hopping over this gap here might actually transfer to the environment over here, where you do have a proper, a gap in the environment. Or the skill that you learn from an environment where you have one of these stumps, right? So here, let's draw in one of these stumps where you have to go over. And if you have a walker that can successfully walk over this, that skill now might transfer over here in order to get over this peaky terrain here. So the idea of Poet is to start off with a generic, flat, very easy environment, and then spawn new ones. So you want to spawn new environments in kind of a hereditary way. So this one might get a bit rougher, this one might include this, and this one might include a gap or something like this. And then again, you want to spawn new environments, and more rough with a stump here, and this one retains the gap, and this one now gets two gaps, and so on. And you want to continuously train these, and then always you want to check whether or not the skill that you learn over here might actually transfer to anyone over here. So you get this continuous tree of solutions, and once you improve on one branch, this might actually be good on another branch, right? They always make the comparison to, let's say, biological evolution, where a strategy that works over here for birds is all of a sudden can be cross-adopted by mammals for an entirely different problem, but the same skill might be valuable. So this is basically the two ingredients of POET, and now I want to show you the complete POET algorithm. So what does it do? You start off with an initial environment, right? And in POET, every environment is paired with an agent. So there is one agent per environment. Right. So for the time steps, what you do is, first of all, you go through your environments and you mutate them. And we already seen these environments, they can be generated from a parameter vector. So we have 5 numbers, right? How rough, how stumpy, and how wide the gaps are. Let's say we have 3 numbers, two, and this might be 1, this might be 2, this might be 5, right? So what you want to do is you want to mutate them, right? You want to spawn children, and each of these parameters has a chance of mutating. This might be 1, 3, 5, and this environment might be 1, 4, 6, and this one might be 2, 2, 5, right? You spawn new ones. You already see that the requirement here is that you can actually have environments that are procedurally generated and mutated like this, where a small mutation probably is going to lead to a small change in the environment. In any case, you mutate them, and then you want to optimize your each agent. So each of these environments is paired with a new agent that always tries to solve that particular environment. So now, within one environment, you simply do your classic optimization. We already saw here the evolution strategy is akin to a classic optimization algorithm from reinforcement learning. Right? So each agent you optimize for a couple of steps, right? Not fully every time, but for a couple of steps. So each agent, including the one in the original environment, each agent is continuously trained on its environment throughout the process. Of course, you have bounded computation, so you need to drop out the very old ones. But in principle, continuously, as all of this goes on, all the agents are always trained on their environments. So the agent here, this walker, will always try to solve this particular environment. And the walker here that is now newly generated when the environment is generated will only try to solve this particular environment throughout the whole algorithm, right? And then, alright, so you do mutations, you spawn new ones, and then you do a couple of steps in optimization, right? An ES step. And then you do this transfer attempts, right? What you want to do is you want to evaluate all the candidates on all the environments in principle. Like you can cut this down, but in principle, you want to go through the environments and say, okay, this environment right here, I'm going to evaluate all of the other agents in this environment. You can do this in a couple of different ways, where you just straight up try them or try to optimize them for a few steps to see whether they can be adapted easily to that environment. But ultimately, you have to come up with a criterion to say, for each agent, is the agent better or worse than the agent that is continuously trained on this environment? If it's worse, then you keep this one. If anyone is better, then you transfer that better one to replace this one, right? And you basically copy it over to this new environment. And that's where this transfer learning comes in. So you're continuously trying all the agents on all the environments. And if they are better, you transfer them, right? So here you say if the environment score is better than the one that you have, you transfer it. All right, now there is a lot hidden here. For example, in this mutate environment step, they do check whether or not the new mutated environments are not too hard and not too easy. And that basically means whether or not the agents can solve them, but not solve them too easily. They also check whether the environments are enough novel. So you need a couple of checks here. Solvable. And that means not too easy and not too hard, right? So they need to pass like a certain score, but they need to be kind of solvable to an okay score. So there's a score range. And also novel. They check whether or not the mutated environments are novel enough. And I believe they just do this by calculating the distance between two environments in terms of their parameter vectors. So to determine whether or not these are novel. And sorry, I don't mean the distance just between two, but the distance of all of the ones you've seen so far. So if we go to our original very beautiful drawing here, where is my tree? If you create a new environment, let's say you create a new environment right here, then you want to check it against all environments you've seen so far to determine whether or not it is new or not. So you want to create the distance to all of these, and if you have enough distance to your nearest neighbors, then you are novel. And that's kind of how they determine whether an environment is new. All right, so that's basically the POET algorithm. You continuously create new environments by mutation. You ensure that they are solvable, not hard enough, not too hard, but hard enough. Ensure that they are novel. And then you optimize each agent for its own environment continuously as the process goes on. And so it's not, I want to stress this, it's not only the frontier. So you're not only looking at the newest generation, but you're always looking at all of the generation of because the older ones, while the environments are easier, they have been optimized for longer on these environments. So the skills might be very handy. So you always want to look at your entire population. And then crucially, you do these transfer attempts. So that's the POET algorithm. There is a lot hidden here, and I kind of want to stress that if you just look at the amount of hyperparameters, there is so many hyperparameters in this. How much you transfer, how much you mutate, how many steps you do. Each of these subroutines here has 1 billion hyperparameters and learning rates and so on. So to me, that is kind of if I look at this algorithm, I'm very scared if I attempted to do something like this myself. It's going to be a long and hard thing to evaluate all of these different hyperparameters that you have to do. Shortly want to dip into what the evolution strategy does, just so you know, because you just might be familiar with your classic reinforce algorithm. So in policy gradient methods, what you do is you scale your parameters of your neural network, which is, you can, if this is your policy, then or your policy network here, you want to scale the gradient according to your reward. So in classical reinforcement learning, this here would be the reward you got, which basically means if you did an action and you got higher reward, you want to make your network do that action more, right? Here in evolution strategies, what you do is you spawn, it's a different way of doing the same thing, basically. You spawn different environments and, you spawn different agents. So you have your current parameters and you want to spawn a number of noisy versions of those parameters. And then you want to evaluate each one, right? And now you want to adjust your parameters into the direction of that particular. So basically, you're here with your parameters. You create a bunch of noisy versions of it, right? And let's say these two performed really well. You want to adjust your parameters into the direction of those two, right? That's basically what this says. So this is the noisy version, and then this is the noise that produced the noisy version. So if this is high, if this number here is high, then you will adjust your parameters into that direction. It's a fairly cool way, especially if you can't backprop through your policy. It's pretty neat thing. So this is the ES step algorithm, but you can think of it just as a RL algorithm. All right, so they do various experiments to show that this actually has some merits. I already shown you, if you take the same environments and try to solve them directly by this evolution step, then it will not succeed because of the problems we've discussed before. Now, the comparison is a bit unfair because, of course, these environments for Poet, the problem here is you can't have it solve a particular environments because the environments, they constantly change, right? You constantly mutate the environments. You never know where it's going. It's not directed. So if your goal is to solve a particular environment, you cannot do it with Poet. You can hope that the agent that comes out will perform well, right? You can do something like this. But I believe that these environments that they test on here are ones that appeared during the Poet run, right? So it's kind of an unfair comparison, I feel, to do this on an environment that, this Poet agent actually comes from an environment that Poet has generated in its all mutation tree curriculum while building it up. And then the poor ES algorithm is simply tasked with solving that particular environment from scratch. So ES, always keep in mind, this can have a goal. This doesn't have a goal, right? That's kind of the drawback. But as you can see, Poet does get super high scores, whereas ES, the classic algorithm, completely fails. And they also investigate the importance of transfer learning. So they compare to like a classic curriculum learning algorithms. There are curriculum learning algorithms where you kind of continuously try to build up the difficulties of these environments, but you also do it in a goal-directed way. So as I said, if you have an environment that has like a gap and then a stump, a high stump or two high stumps, you want to start out flat and then maybe build in a small gap and a small stump and so on until you're here. It's very much goal-directed. But it doesn't have this kind of population with transfer learning aspect of Poet. So if they compare this, you can see here the red one, sorry, I colored it blue stupidly. The red one is whatever Poet was able to solve. Now these are the 5 dimensions of the parameters, and the more on the outside it is, the harder the environment. And for the same environment, the blue one is what the curriculum learning algorithm has managed. So it's the best environment the curriculum learning algorithm has been able to solve while trying to build up to the, so if we take this here is the environment that Poet solved. Again, the comparison is kind of unfair because we're starting out from an environment that Poet has already solved, and then we're trying to build our way up to it with the classic algorithm by basically, again, it's comparing a non-goal directed thing, something that just happened, to a goal directed process that needs to get this particular environment to work. In any case, at some point this curriculum learning algorithm will fail, like let's say that's here, that's the environment that has somewhat of a gap but no stump, right? And that would be the blue line here. They do like 5 runs and they plot them here, and you can see every time the classic curriculum learning algorithm manages to only solve a much less challenging environment than the Poet algorithm achieved, even though it's trying to reach exactly that, right? And so here they show the difference. So if you just classify the environments, if it's just challenging, then the classic algorithm, the curriculum learning algorithm, can solve it somewhat, so the distance is close to 0. But as you go more and more challenging, the distance between Poet and the classic algorithm becomes larger and larger. They do give some examples of what this transfer learning does. So they have this parent environment that just kind of slouches forward on the ground, and then the child environment has a mutation that has now little stumps in it, right? So it can't get over it right now. But the child environment, because it's a small stump, so it might stumble across, learns to lift its leg here, and it transfers this back to the parent, right, at a later iteration, which is pretty cool. And then the parent gets even better as a result of that transfer. So we have 2 transfer learning events here that mutually help these agents. Remember, both the parent and the child are continuously trained as the process goes on. All right, and they do some more things where they do actual Poet, not a classic algorithm, but Poet without transfer learning, and they see that, okay, the Poet without transfer is able to solve some of the very challenging problems, but never reaches the extremely challenging stage, and that's kind of their argument why the transfer learning is necessary. So in total, I would say this is a cool algorithm. It has many hyperparameters, and these experimental results with that many hyperparameters, you need to take it with a grain of salt, because it's always possible that they just haven't put as much effort into the comparisons as they have into their own thing to get it to work. All right, with that, I wish you a nice day, and check out the paper. They have lots of descriptions. Check out the blog post where they have animations and a YouTube video. And with that, bye-bye.